Hello, everyone. Welcome to the programming seminar series, day 3. So today is the final day. I'm Yasasya. Last 2 days went really well. So today we have introduction to deep learning. If you attended the previous seminars, I think you are quite familiar with the format that we operate. So this is the 1-hour session, and the seminar will be recorded, and you will have the access for the recording as well as for the slides. You can use the chat option to ask questions, and you can wait till the presentation end to ask the questions as well. So you can unmute yourself and ask the questions. You can have access to previous slides and previous seminars in our GSG website, and you will have the access to this seminar series, the recording of the seminar series, on next Monday. And for those who participate today, I would send the recording and slides to you today. And we expect your feedbacks and suggestions. You can email it to the Professional Development Chair's GSG email. So today, Dr. Timothy Havens is going to present about the introduction to deep learning. So without further delay, I will give him to lead the presentation on.
Hey everybody, welcome back, or hi if you missed Tuesdays. I hope you enjoyed the R seminar yesterday. I posted a link in the chat that has a template that we're going to use. But first I'm just going to give a little introduction to deep learning, and then we're going to go through a programming exercise, and I'll stick around for any questions that people have, just like we did on Tuesday. So I hope everybody's doing well. I see we don't have as many people on today. It must be because the weather is just absolutely amazing. So after this, you can go swim in Lake Superior. But until then, we're doing deep learning. All right, I'm going to share my screen now. If you have questions, chat them in the chat box, or just talk, and we'll get to them. Okay, should be able to see this. All right, so deep learning. So deep learning is obviously very fashionable right now. I think that even if you talk to your parents or talk to your friends who are not scientists, they will have heard of deep learning, and perhaps even have some misconceptions about what it is or what it can and can't do. And hopefully at the end of today, you'll have a decent understanding of what it is, and we'll be able to get started in using it and find that it's fairly easy to do, but it's also very easy to screw up. So, okay. So something that many people have heard about is AlphaGo, and we talked about this on Tuesday too. But in 2016, Google's DeepMind project produced a computer program, AlphaGo. A big part of that is a deep learning network, which can beat the best human players in the world, and showed that by beating Lee Sedol, who is the best Go player in the world, or the leading Go player in the world. And then later on, they produced later versions of AlphaGo that didn't even learn from humans. It just learned by playing itself and even became better. So I think it shows that even in this case, the human data wasn't nearly as good as just producing the data from the artificial intelligence. So deep learning is a big part of this. It's been a big thing for a while. Certainly the backbone of deep learning, which is neural networks, have been around forever. But you can see here in the technology review in 2013 at MIT, you know, they recognize deep learning as kind of like the top breakthrough technology. And I don't know, I hesitate to call it a breakthrough technology. I think it's neural networks back again. So neural networks had their big heyday kind of in the 80s, and then they realized that there was some inherent problems, and then computational skill caught up, and now we're back to doing neural networks again. And so speaking of neural networks, so deep learning, all it is just a whole bunch of neural networks stacked on top of each other, hence the word deep. And so we'll talk about that a little bit. I'm not going to get into it too much. But Isa asked a question on Tuesday, you know, isn't classification just regression when it comes down to it? And absolutely. So you can see that neural networks, when it comes down to it, is also regression. It's a linear model, and regression is just an equation of a line, really, when it comes down to it, or a hyperplane, you know, if you're into high dimensional stuff. So you can see over on here on the left, we have some inputs, these A's that are going in. We have a bias input, whether it's -1 or +1, doesn't matter. You're weighting each of those inputs on the left. Those are summed up. So you can see this is just like W transpose A, which is just an equation of a hyperplane. The activation of that, or the output of that function, goes into an activation function, which maps this to a nonlinear surface. So this could be like a logistic regression unit. So for example, if it was a sigmoid function, this neuron would be a logistic regressor. And so things on one side of the hyperplane would be up in the top of this curve. Things on the other side of the hyperplane would be in the bottom part of this curve. Then we have some output, and then that output links to other neurons which look exactly the same, and you just do this over and over. Even convolutional neural networks are just like this, because a convolution is linear when it comes down to it. So it's the same thing. The activation functions can be different, whether you're using sigmoids, which are logistic regression activation functions, this was shown on the right here, or step functions, which are kind of the hard side function. Rectified linear units are really popular, and we'll use those today in our example. But there's things called leaky RELUs, and man, there's a billion activation functions. If you search through the Keras documentation, which we're going to use Keras today, you're going to find that there's a bunch of them. There's a lot of limitations of neural networks. Initialization, so they're not a convex optimization problem. So there are multiple solutions, and not necessarily even one unique best solution. So training them can be challenging. You can get stuck in local optima during the optimization, which is usually done by gradient descent. Backpropagation is what it's called. So random initialization doesn't guarantee that you get to the same solution every time. They're difficult to train as the number of layers increases. So there's this thing called vanishing gradients, that as you go backwards through the networks, the deeper they are, the smaller the gradients get at the beginning of the networks. And so that can be challenging. Extremely high cost in computation and energy. In fact, they trained a program to play the game Dota 2, which is kind of like, it's a League of Legends, if you've heard of that. It's a real-time strategy game. It's a computer game. And they trained a deep network to play this game, and it was very, very good at the game. But it took the equivalent amount of energy to train this network as like 5 car lifetimes. So just the average car driving around, you know, for the lifetime of the car, and it was that much energy. That's a ton of energy. And so, you know, that's becoming a big thing with deep learning right now, is trying to find efficient ways to train them as well, because the networks are getting more complex. They're getting higher cost to train, higher cost in energy. And eventually, you know, we'll just have to donate our atoms to power these things to train them. And we don't want to do that just to play a computer game. So that's silly. So there will be a reckoning of deep learning. So why do we do this though? So there's new algorithms in theory that are good at learning weights for these deep networks. So kind of the learning theory and the algorithm development came a long way since the 80s. So we're able to attack problems like the vanishing gradient problem. And then also there's new, I didn't put this here, but computationally, you know, our computers are just that much better than they were back in the 80s. So we can actually have the computational power to solve these things. And they really combine together ideas of both unsupervised learning and supervised learning. And I'm not going to dig into the learning so much. I just want to, you know, kind of introduce you to what deep learning is. Then we'll go through an example, and I think that'll be the best for this. Assuming I'm not assuming anything of the clientele on the call here. I assume you can code in Python. So, but how do deep learning networks work? So essentially what they are is just layers of feature learners. So you can think about until the very end of the network where some decision is made. Before that, what they're really trying to learn is how do we represent the data that's given to us in a way that when we get to the end of this network, typically there's going to be a logistic regressor, a standard linear logistic regressor at the end, almost always. And so we need to figure out a way to project up the data from these data, whether it's pixels in an image or time samples in an audio waveform, into a high dimensional space such that when we find our separating hyperplane in that high dimensional space, that cars are on one side of the hyperplane and cats are on the other side of the hyperplane. And so in this case, deep networks do this in levels. So you have low-level features. So this is just showing what these convolution kernels look like. And we're going to do this in our code today too. I'm going to show you how to do that. But you can see each of these convolution kernels are looking for different things. So whether they're like diagonal edges, you know, in these, or difference in color gradients. You can see the color gradients in some of these. Then they go to mid-level features, which start to be like combinations of these low-level features. So it's things that start to look like you can see like an eyeball in there, or maybe that's like a wheel of a car, etc. Or textures, you know, whirly textures or linear textures, or I don't know, this kind of looks like grass. And then we get to high-level features, which then are like textures put together to produce more like imagelet type things. So you can see, I don't know, like maybe spokes in a wheel right there. So definitely some wheel-shaped things up here at the top. I don't know, this maybe looks like the grill of a car, the front of a car. Some lettering, maybe with a keyhole. I don't know, stork head. I have no idea where a stork head comes in trying to recognize a car, but maybe that's cars versus storks. Who knows? A honeycomb pattern. So on and so forth. And so these patterns then, as you go through, then come up to be a car. I mean, this one right here in the middle at the top, that looks like the front of a car. So it's probably a specific type of car. Convolutional neural networks just stack up these convolution kernels until you get to the end, where you have some multi-layer perceptron, or logistic regression is what it really is at the end. And we'll fool around with that. We're going to do this stuff in the example that I have planned. So just to kind of show you the example of what happens with a convolution is that there's some kernel. So the kernel is the little numbers in the lower right of this image. And then the convolution just takes place when you multiply each of those numbers in the lower right by the numbers that it finds in the image, adds all those up, and so then you get the results in the convolved feature. So you can see what's great about convolutions is they can represent spatial content in an image, which an image, that's all it is spatial content. And then you can take that spatial content and start to recognize certain types of features in that spatial content with this convolution kernel. Another great thing about this is a linear operator, because it's just one vector of numbers times another vector of numbers. So this is just W transpose X, where W is the weights of the convolution kernel and X is the pixels underneath that convolution kernel. It just happens by swiping over the image. And that's how TensorFlow works. That's why it's so fast, is it takes advantage of the way that processors are really good at computing basically dot products. not just basically, but explicitly dot products. Okay, another thing that happens in deep networks is called pooling, and pooling is a way to take features and sum them down to one number. So you can think of pooling as like a convolution where you'd have like all ones underneath it. That's like sum pooling. But there's also nonlinear pooling layers called like max pooling. Max pooling is used quite a bit. What you do is you just take the max number underneath each of those squares and then pass that down. And we're going to use max pooling in the example that I'm going to show. There's some really good data sets out there for this. So ILSVRC, if you look for ImageNet or ILSVRC, you'll find these. So it stands for ImageNet Large Scale Vision Recognition Competition. There's one every year. And so I'm just showing some examples from one of the recent ones where you had to tell the difference between breeds of dogs. And so you can see the Entel-Bucher and the Appenzeller. They look almost exactly the same. And so that you can see that that's a very challenging image classification task. Okay, so let's kind of look at some example structures. So this was back in 2012 with the ImageNet. AlexNet was created, and AlexNet you can see was, it had 1, 2, 3, 4, 5, 6, 7, 8 layers. 8 layers, pretty tiny actually, and that's about the size we're going to work with today because we can do it fast. AlexNet was the winner of ILSVRC, had convolution layers and some fully connected layers at the end, and the idea was that you had to take an image and classify it as one of 1,000 classes. And so ImageNet is used quite a bit to train networks. Later on, in 2014, you can see VGG was the winner, and it had 19 layers. GoogleNet in 2014 was another winner. It had 22 layers, and there were some definite innovations in GoogleNet, and it is pronounced GoogleNet because Jan LeCun was part of the team that invented GoogleNet. So you can see this is called like a residual network. And then later on, if you go forward in time, like ResNet, which actually ResNet is chugging on the computer behind me, is 152 layers there. And so you can see as that score went down, and you can see this is just the error score, so a small error is a good thing, then the number of layers increased. So it's 152 layers versus 8 layers. That's a big increase in layers. So you can see that networks are growing exponentially. That means exponential growth in energy. And so it's a big thing. There's some cool things in deep learning that I just wanted to kind of put this picture in there. This is called Google Deep Dream. And what the idea here is that since these deep convolutional neural networks, the things that are in these networks represent images as just collections of these convolution kernels, you can actually work backwards through the network too, and you can reconstitute image from these convolution kernels, and you can choose certain kernels to reconstitute images. So this is an image of a cat produced from, I think it's like dogs and fish and stuff like that. So if you squint, it looks almost exactly like a cat, or if you back way up. But if you look closely, you're like, whoa, that is really creepy. It's like one of those movies where like the demons are inside of you. Perhaps a little deep for this one. It's a deep dream. They say they have deep nightmare and stuff like that, and I don't know, it's probably like pictures of Donald Trump. So you can use Deep Dream. So I give you the GitHub site where you can go download it and try it. There's also online versions. If you type Deep Dream, there's visualizers online that you can use. But it's really easy to use your own code, and then it works a little bit better in my opinion. So Deep Dream is cool. So that's kind of the end of my introduction. I really want to get into the coding example because we can kind of talk through things as we do that. So what I want to do now is I'm going to stop sharing. If you click on the link that I gave you, it might come up and it might not look quite good. So you might click on it and then it looks like this. And so the first thing that you're actually going to want to do is go up to the top here and say open with Google Colaboratory. So if you open this and it just looks like a bunch of text, That's because I think it was just the way that I took this file and copied it across the computer, and then Google doesn't necessarily recognize it as a Google Doc. If you say open in Co-Laboratory, then it should open right up and look like that, which is nice. Okay, so the next thing that you're gonna have to do is go up to File and save a copy in your drive. So if you go up to File, click on that, and then save a copy in Drive, then you should have a copy that's saved. So this is where what it should look like here. What we're going to do here is we're going to do some deep learning with the MNIST data set, and we're going to look at some images from MNIST. These are 28 by 28 pixels images that are extracted from zip codes on United States Postal Service envelopes. This is a really old data set, and it's been used for a long time. I think the first time it was like published in 1995. I can't remember exactly, but it's really old. So click in the first cell here where it says import libraries, and just click Shift Return in that cell, or click on the play button. And what this is doing is we're going to import the NumPy library. So I like to call it NumPy. I think it's probably NumPy for Python, but NumPy's funny. This is a great library for doing matrices and arrays and math with matrices. So it's wonderful. And then I'm just initializing the random seed there in the year that Michigan Tech was formed. And then we're loading TensorFlow. So from TensorFlow, import Keras. So Keras and TensorFlow are now integrated, which is awesome. It makes it really, really easy. And then from TensorFlow Keras, we're going to import layers, which are the different layers of the deep learning. So Keras has MNIST built in, so it's great, it's wonderful. And so we're just going to load it right from Keras. And so if you hit Shift Enter in the next cell, it's going to load Keras. And then you're going to see it's going to load the two different data sets, the training data sets and the testing data sets. And then we're just going to set the num classes at 10, because we know this is digits, and we know the number of digits is 0 through 9. We're assuming base 10 zip codes. Okay, so it shouldn't take too long. We're all using Google Colab, I assume. So it took 2 seconds. It's wonderful, it's loaded. And so now what I want you to do is, I want you to print the shape of X-Train. So I left this blank because you should have gotten this on Tuesday. So just print the shape of X-Train just to see what this data look like. And so you should see that it has 60,000 rows and then 28 by 28 images. So each of those rows of X-Train is a 28 by 28 image. So this is a 3-dimensional array. And so let's kind of look at it now. So we're going to use matplotlib again. So we're going to import this pyplot as PLT. And so let's insert the code here to just look at one of these images. So plt.imshow x_train, and we're just going to do the 0th element. This is one of the great things about Python is you don't need to be explicit about the other 2 dimensions. It'll just automatically load those 2. And if you have what looks like on my screen and hit Shift Enter, you should be able to see the first datum in X-Train. So what number do you see here? 5. T. T is not a number, Kevin. But I think you just, yeah. I think, Kevin, you just, yeah, that's actually what I was going to say. You fat-fingered a 5. There's some good responses there. You're definitely showing that you're human. Okay, so there's some really good ways now to work with these data. So TensorFlow and most other deep learning packages kind of require it, data in a specific size. I see a typo there, so I'm going to fix that right quick. So convolutional, oh, I'm getting even worse. There we go. So they like to have data in N by width, by height, by number of channels. So the number of channels is the number of colors in an image. So it's natively set up to be either one color, 2 colors, 3 colors, or even multispectral or hyperspectral. So in this case, the number of channels in these images is just 1, because it's just intensity. These are grayscale images. All that they did is they took a black and white or grayscale camera and took pictures of these images. So we need to expand the number of dimensions such that that dimension exists, or else TensorFlow is going to give us a problem. So it's great because NumPy gives us a really easy way to do that. And so you can see here we're expanding the dimensions in NumPy just by putting this expand dimensions -1. And so what that does is it just automatically adds a dimension onto the end. If we were going to put a positive one there, it would put the dimension on the beginning. So then we're going to print the shape again, and then we're going to say, okay, the input shape for the network is going to be 28 by 28 by 1 channel. And we know that now. We've looked at the shape of this thing, we added the dimension. And so you should see now, okay, the shape of this thing is 60,000 by 28 by 28 by 1. Now that 1 dimension is empty. There's nothing really there, but it's required for TensorFlow to work with these data. Okay, another thing is that these data are int8. So they're 8-bit integers, or integers from 0 to 255. These don't work very well with TensorFlow natively. You can run into problems. So the first thing I always do is just convert to float 32 values on the range 0, 1. You don't need to use range 0, 1. Some people like to normalize in different ways. You could, for example, you could subtract the mean and divide by the standard deviation. That's called z-score normalization. We're just going to put them in 0, 1. It works really well. Some GPUs can use float 16 too, which can be great because you can fit twice as much data in your GPU. These aren't very large, so we're just going to use float 32. So when we normalize the data, first thing we're going to do, we're going to cast these as type float 32. That's just great Python right there. And then we're going to divide equal by 255, and this is now, since we know that 8-bit integers are from 0 to 255, if we divide by 255, we're now from 0 to 1. Do that. Make sure that that ran. Okay, let's look at a few images now. And I said, did you get an error? And so let's run this and see what happens. And so I built an error into this, is what happens. Okay, so if you ran the cell that starts with plt.figure, what this cell is doing is it's doing a for loop, and in the range 0 to 9, which actually in Python ends up to be the integers 0 to 8. Range 9 is 9 integers. It doesn't mean the n integer, it's 9 integers, 0 to 8. And we're going to do a subplot, a 3 by 3 subplot. We're going to do what's called a tight layout. And then we're going to show these in a gray color map, because you can see up here, this is not a gray color map. That's that kind of standard color one they use. No interpolation, whoops. And then we're going to give it a title, which is going to be the digit. And so you can see we're getting the digit from the training label, this Y train, and taking off the axis ticks just with an empty variable there. But what happened is, if you go down here, it says type error invalid shape 28281 for image data. And that's true. It's like, it's saying like, no, I can't plot a 3-dimensional image. This doesn't work for me. So what we can do here is we can use a command. So right before this X train, I even put the parentheses around there for you, do np, which is npy.squeeze. What this is going to do is it's going to squeeze off that empty dimension and leave us just with 28 by 28. So if you do that now, awesome. Now we see these lovely numbers. You can see the labels above them, which obviously match the numbers. And so that's wonderful. We can look at our data. Okay, everybody with me? You good, Isa? Emily, Kevin, Sahil? Awesome. Thank you. Oh man, look at these responses. It's like teaching in class. Okay, so now let's look at our class labels. So far what we did is we looked at the feature data, which are these images. We started to look at the class labels because I put them here. But let's look at the shape of our class labels. So let's just kind of put something in here so that we can see those class labels. So the class labels are in y train. So underscore y, or excuse me, lowercase y underscore train dot shape. Okay, so we have 60,000 class labels. Makes sense, right? We have 60,000 images. So let's kind of just print out the first 10 of those too. We can do that by print y underscore train, and then we do square bracket :10. This is another great Python thing that, you know, if you do :10, it just interprets that as 0 to 9. It's wonderful. We do that. So awesome. We get 504, 192, 1314. You can see those actually match those up here, except we're printing out 1 and 1, 2. So this is what the labels look like. Now, this is actually a problem for classification. So these are stored as vectors of integers rather than vectors of categorical class labels. So with classification, you know, the class labels need to be categorical. So this is really easy to fix, again, because Keras is built for this. You can use the Keras utils library, and so we're going to convert these to one-dimensional class arrays to 10-dimensional class matrices. And so all that we're going to do here, we're going to define a new variable uppercase y, because now these are going to be matrices as opposed to vectors. Train and test, and then we're going to use keras.utils to categorical. Man, it's like they designed this to be readable. Y train, and then the number of classes that we have. And this is just automatically going to take those integers. You hit Shift Enter there, or the play button, and change those to our labels. So let's kind of look at these. Let's print the shape of this now. So now we're doing uppercase Y because we have this new train matrix. So let's print the shape of that and simultaneously print, you know, the first 10 labels. Okay, so this is what our new class label output looks like. Rather than 10 integers, we now have a 60,000 by 10, and these are binary labels. So the first column represents the label 0. And so if we go up here and look at this, in fact, that second datum is 0. So we can see that second datum right here as a 1 and the 0. Second column represents 1, 2, 3, 4, 5, 6, 7, 8, 9. And so if we look at 9 here, we see that the fifth datum has a 1 and the 9. And if we go up here, in fact, yes, it is a 9. So this is just a different way of representing those class labels. And this is what TensorFlow expects. So this is what we needed to do. Okay, are we all good? Everybody has all these run up to this point. If you haven't got these to run, you're gonna have trouble with the next step. So make sure that you have all this stuff to run. I'll kind of wait a second while people are getting going. Okay, I see lots of smiley faces and thumbs up. And Zach, is that you? Is that my Zach? Oh, no. I have a PhD student named Zach. I'd be surprised if he was here. He does this as research. I mean, he'd probably be like, oh my God, this is stuff I do every day. So nice to meet you, Zach. Okay, so now let's make a model. We're going to make a deep learning model. And I'm going to kind of lead you through this slowly so you can kind of see different ways. And so the first thing that we're going to do is we're just going to start by adding our first 2 layers. And I'll talk about what those layers look like. And so the first line in this down here, model equals keras.sequential. So what this does is it initializes the model to a sequential model, which means that there's a single path from the input to the output. So you go from the input all the way to the output in a sequential fashion. This doesn't necessarily mean that there isn't, like, you know, jumps and stuff like that. It doesn't, but it's another way to say this is it's a direct acyclic graph, directed acyclic graph. And then what we're going to do is we're going to start adding layers to this model. And so the first layer, almost always, it doesn't necessarily have to be, but it almost always is going to be an input layer. So this layer is going to be designed to take some input from outside of the network. And so here we got model.add. And so what this means is we're going to add to the model keras.input, and the shape is that input shape that we already set. And so we already set that to be 28 by 28 by 1. We set that way up in the code. Then we're going to add a convolutional layer. And what this convolutional layer is going to be is it's going to be 3 by 3 kernels. So remember I showed you that example of convolution passing over that matrix. It's the same thing. That was a 3 by 3 convolution. This is going to be the same thing, a 3 by 3 convolution, kernel size. But rather than just one of those things passing over the image, we're going to use 32 of those things in the first layer. So that means that we have 32 different kernels that pass over the image in that layer. The result of each of those convolutions is going to be passed through what's called a rectified linear unit activation. And so a rectified linear unit is really simple to explain. So everything less than 0 is going to be made 0. And then everything that's a positive number just passes through the rectified linear unit unmodified. So it's basically, you know, y equals x if x is greater than 0 and it's 0 else. That's simple. That's a rectified linear unit. It imposes nonlinearity due to that nonlinear, that piecewise construction of the network, of that activation function. So we could run this cell, and now what we've done is we've created a model. This is now a deep network, albeit it is the shallowest deep network you can have of one layer. So let's kind of think about this. What we're doing is we're passing in an image that's 28 by 28 by 1, which just means it has one channel. We're going to have 32 3 by 3 kernels that we're going to pass over this thing, and then we're going to get the outputs of those into a new output out of that. So what we can do is we can say, okay, what's the output shape of this model? So if we hit Control Enter on that output shape, we see first we have none, we have 26 by 26 by 32, and so that let's go through that. So this first none, this is kind of a placeholder because the model is built to handle multiple images at once. So if you pass in multiple images into this model, that would actually be the first dimension. So if we think about our MNIST data itself, it had 60,000 images, and those were 28 by 28 images. That if you passed all 60,000 at once, then this would turn into 60,000. So right now, the output shape is just saying none because you don't know what that shape is going to be until you actually pass data through. The second two, we have 26 and 26. So I'm going to ask a question back to you. We passed a 28 by 28 image in here, and we did a 3 by 3 convolution on these images, and now we have 26 by 26. Why did a 28 turn into a 26? Edges. Yeah, because we can't take, in order to have that 3 by 3 kernel on the image, we have to have some edge pixels in order to have that centered on the pixel that we're currently considering. So if the center of that 3 by 3 is where that output spits out, then it has to have something on the edge in order to compute. If this was a 5 by 5 kernel, it would reduce again. You know, we'd have a 24 by 24. In fact, we could verify this. We could change this to 5 by 5 up here, run that again. And if we run this again, we should see that this turns into 24 by 24. And that's because we lost yet another edge. So we'll make that 3 by 3 again. We want to keep that 3 by 3. And then you can see finally the last is we now have 32 channels rather than just one channel. And that's because this convolution is done 32 different kernels. So now each of those kernels turns into a new channel. So you can see the new output on this is, you can consider this to be like a 32 channel image where that image is 26 by 26. And in fact, we're going to look at those channels later as images to see how this works. Okay, so this is one way that you could build up a network. So we could even, we could add another layer here by just, kind of stacking these up like this. Whoops, add. But there's an easier way. and a faster way. So if we go down to this next cell here that starts with model equals keras.sequential, what I'm doing now is I'm just going to do it all at once. We're going to define our network all at once. And so we see model equals keras.sequential parenthesis. And then in our square brackets here, we have an array. So that's how Keras represents these models. It's going to be an array of layers. So first we have the input layer, just like we did above, which has the input shape of the image. Then we're going to have a convolutional layer, which is exactly like the one that we applied up there. Then we're going to have this max pooling layer. We're going to use a pool size of 2 by 2. So this max pooling, all it does is it takes that 26 by 26 image and passes over that in 2 by 2 chunks and passes out the maximum number in that 2 by 2 chunk. So really what it's doing is it's kind of binning this image down by using a max operator. And max pooling is a really important piece of deep learning, because what it does is it basically says, I don't care where the activation happens inside that convolution kernel, I'm just going to take the max activation. And it's actually shown through theory that max pooling helps with things like with scale invariance and rotation invariance and translation invariance. So max pooling is something that works really well. So after that, let's add another set of conv2D and max pooling layers. This time we're going to use 64 filters though instead of 32. So a real easy way to do that, just highlight these right here. I'm going to copy them, go down here, paste those in. And so rather than 32 filters here or channels, I'm just going to change this to 64. Keep the kernel size the same, keep the max pooling size the same, and we've just added another 2 layers. So you can see it's actually really easy to kind of build these up as you get good at it, because you can kind of copy and paste things through. The next layer that we have after that is called a flatten layer. And what this basically does is it takes the output shape of this final max pooling here, and it flattens that down to one really long vector of numbers. So it doesn't care kind of what size or the number of channels that you have. It's just going to take all those square little images and the number of channels and flatten all those down to one long vector. Then what we're going to have is what's called a dropout layer. So dropout 0.5, this helps with training of the network, and it helps with generalization. So a dropout layer essentially, as you're training, randomly drops out, in this case, half of the numbers in that big long vector. It's going to say, okay, we're just going to set a bunch of those to 0. And it helps with generalization. There's a bunch of papers out there that you can read on this, but dropout is really good, especially when you want to have good generalized performance. Finally, and this is typically the last layer in deep convolutional networks or deep networks period, is what's called a dense layer. So what a dense layer means is all this is your standard neural network. So this is your one node or how many nodes that you need in order to get outputs in neural networks. The number of outputs is the first argument here. And so the number of outputs now is going to be the number of classes. So we're going to get one output for each class. And then we're going to have what's called an activation, is the soft max. And all that soft max does is it looks for the max of those 10 outputs and then outputs that as the class. So each of those is going to be a score of each of the 10 classes, the 10 digits, and then soft max is just going to output the highest number. It's just a standard one layer neural network. Okay, so now that we have this, let's shift enter on this. Model.summary is going to print a summary of this network, and then that shows you the full network. So we go in, we have the first, it doesn't show the input layer. So it's going to have the convolutional layer. You can see the number of parameters that are trained in that convolutional layer. So we have 320, and that's because we have 32 channels. So if we divide this by 32, we'd have 10. And then we have a 3 by 3 kernel. So that's going to be 9 numbers in that kernel. And then one more number for what's called the bias. And so if you think about the equation for a line, it's W transpose X plus B, or MX plus B. So there's a bias in there as well. There's no parameters in a max pooling. In this next convolutional layer with 64 channels, we have even more parameters, and that's because, you know, we have these 32 channels, these 13 by 13 images. It's going to do 64 of these on each of the 32. So you have 64 times 32 times 14 times 14. You should get about that number right there. Another max pooling. There's no parameters in a flatten. That's just kind of reshaping all the numbers. There's no parameters in a dropout because that's just a training thing. And then finally in our dense layer, the number of parameters in the dense layer, if you divide that by the number of outputs, so in this case, if we divide by 10, 1,601, that actually gives you the total number that are in this flattened layer. So you can see here, we have the 1,600. Again, we have the 1 because of the bias. We always have that bias number on there. And that gives us the number of parameters in the dense layer. So a total number of parameters in this network, 34,826. 34,826. That is crazy. So you have a data set that is 60,000 examples with 34,826 parameters. This should be able to do fairly well on that data set, right? If you recall, like, you know, as the number of unknowns approach the number of equations, you know, then you can do well in fitting what those unknowns are. Now, this is a very small network, a very, very, very small network. So imagine what, you know, what ResNet 101, how many parameters that has. You could look it up. That's 101 layers. This is like 5. So crazy, crazy. Okay, now that we have this, everybody should be to this point where you can see this, this model summary here. Let's do some training. So going down here, what we're going to do, we're going to set batch size equals 128. What this does is this is the number of images that it considers at each time it updates the network. So all of these things are just gradient descent learning. So it's going to take 128 images, put those through the network, figure out what the gradients are, back propagate those to change the weights in the network, all 34,826 of those parameters. Do that over and over and over. Epochs is 15, which is the number of times we're going to cycle through this 60,000 size data set. So we're going to go through this data set 15 times, and we're going to compile our model. And what this does is it gets it ready for training. So the first thing we have to do is we have to give it a loss function. So this is going to be the performance metric. You know, we have to have something to calculate gradients against. Categorical cross entropy is what's typically used for classification or multi-class problems. So what this does is it works really well for classification problems where you have more than 2 classes. The optimizer we're going to use is, or how do we compute the update to the weights, is called the atom optimizer. This is derived from adaptive moment estimation. It's not an acronym. A lot of people think ATOM is an acronym. It's not. It's just a name. It's just a fancy gradient descent approach. Another one we could use is stochastic gradient descent. That would be SGDM. But ATOM works pretty well for this example. And then we're also, this metrics here, all that it means is, since we're going to give it verbose output, we're going to see output as this thing is training. We also want it to show the accuracy, or how well this thing is doing as it trains. Okay, the next line, this model.fit, that's the training line. This is going to take the model, take the training data, and fit it. So the inputs to that are training features. So X-train is all those images, so 60,000 images. Y-train is that matrix that we made of the 10 labels for the 60,000 images. Batch size equal batch size, self-explanatory. Epochs equals epochs, self-explanatory. Validation split. So what this does, validation split takes the data. It's going to randomly take 10% of those data, so 6,000 images, and kind of hold those aside and calculate the accuracy and loss on that validation split as you go along. What this allows you to look at is if the network is starting to overtrain. Because if your validation accuracy starts to go down, or on that data set, then you know, like, okay, I'm training too much. Okay, so let's hit Shift Enter on this. This is going to take a little bit, not that long, but it's going to take some time. Just kind of talk through this as it's going along. So epic 1 of 15, you can see it's shooting along. Oh, I forgot something. Let's stop this for a second. In order to go this fast, you need to do something. So this is a trick in Google Colab. You want to go up to runtime. So everybody go up to runtime, click on runtime, go down to change runtime type. And it may already have been changed because you copied the template from me. If you go to change runtime type, you're going to want to go to hardware accelerator equals GPU. If you don't use this GPU hardware accelerator, it's going to be slower. So you can use GPU hardware accelerators in Colab. They have TPUs too, although I don't recommend using that. Then just hit save on that one. Was everybody's already set to GPU? I'm curious if that setting gets passed along when you copy a template. Probably does. Okay, cool. So anyways, hit Shift Enter on that again, and we'll start our training again. So you can see this works fast. So even after the first epoch, the validation accuracy is already 99%. You know, it went through this data set once, and it's already up to 99%. But you can just, or 98.6%. How about that? Like, you know, what your temperature, I guess, is supposed to be. Although I read an interesting article about standard temperatures. So we all know that like the standard human body temperature is 98.6 degrees. But actually that's based on historical data and really old historical data. And in olden times, people were constantly sick. So basically everybody kind of had like a low grade fever running all the time because, you know, they only lived to be like 40 years old. And so 98.6 based on historical data is actually high, and that our true standard temperature should be about like 97.5, which is probably why most of you, when you take your temperature, it ends up to be in the 97s as opposed to 98.6. So there you go, a little trivia. So, okay, so everybody should have gotten through their 15 epochs at this point. You can see this was super fast. We just processed a data set that is 60,000 28 by 28 images, and we did that 15 times. And you can see at the end here it has a validation accuracy of 99.3%. So it can look at these images and tell you to a degree of 99.3% of basically zero errors. You know, that's crazy. Okay, so we have some test data that we haven't looked at. So the MNIST data has a built-in test data. So it's 60,000 images that you train on, then it's 10,000 images that you test on. And so now let's bring in those test data in the next cell. We're going to evaluate, model.evaluate, just takes our current model and evaluates on data. And then we're going to look at how well this did. So you should get something in the 99% accuracy. So this is data that is never seen before, and it's 99.2% accurate. Just absolutely cool, absolutely cool. Okay, so we have a few more minutes left, and what I want to do in the last few minutes is I want to show you kind of let's visualize what this network looks like. So the first thing that we can do is in this next cell where it says retrieve weights from the second hidden layer. So we're going to take the weights from that convolution layer, which I call it the second hidden layer because the input layer in historical sense is like the second layer, although you can see that's layer 0 there. Kind of ignore that. And we're going to use get weights. And so what it's going to do is it's going to pull those parameters out of that layer. And so if we go up here, we can see, you know, there's 320 parameters. It's those 320 numbers, and we're going to visualize those. So the first thing that we're going to do is we're just going to say filters and biases. We're going to ignore the biases and not look at those. We're just going to look at those filters, those convolution filters. We're going to normalize them to 0 and 1. I show you the code there. Then we're going to plot the first few filters. So I have, you know, 16 here, but let's just do we know that there's 32. So let's look at 32 filters. So change that end filters to 32. Rather than a 4x4 plot, let's just do a 4x8 subplot. So change that to 4,8. And now it should just work. If we hit Shift Enter, Uh-oh, invalid shape 3, 3, 1 for image data. Oh, but we already know what we need to do there. Remember that NP squeeze? Give it an NP squeeze. Socially distant hug. Okay, those are those 32 convolution filters from that first convolution layer. So looking at these, when you see the white pixels, that means that like that's a big number. So any pixel that's underneath that pixel is, and if it has a big number, it's going to get multiplied by a big number and cause changes. So you can kind of think of convolutions as that things that look like the convolution are going to cause big changes in the convolution. Things that don't look like the convolution are going to cause smaller changes. So this upper left one, this is kind of looking at like structure that looks like this, where we have, you know, kind of like a diagonal edge that maybe is getting brighter as it goes along towards the lower right. I don't know, this H form here, the second row, first column kind of looks like it looks like it's looking for like a horizontal edge that's going from bright to dark, from top to bottom, and so on and so forth. So it's kind of cool is that it kind of shows you what's it's looking at in there. I mean, we could do the same thing with the other convolution layer, which should be, we have a max pooling layer. It should be 0, 1, 2. That one's 64. I don't know, let's show 32 of them now. Let's see if this works. Oh, it doesn't like that. Well, it didn't like that, so I don't want to waste too much time, but yeah. I do show you a way that you can. So now we can also look at how these convolution filters affect the data. So this was data independent, but we can actually take an image and we can put it into this network and start to look at it. So the first thing that we're going to do is we're actually going to create a new model. And the new model is just going to be the old model. So we're going to use keras.model, where the inputs are going to be the model inputs, and then the outputs are going to be the outputs from that one layer we want to look at. And I'm setting layer equals 0 here. And so if we just hit Shift Enter on this, you can see we have a new model that we've just created. All that I've done is just take the old model and kind of chopped off part of it. And so as an input, and then the convolution layer. And what we can do now is we can take our images and pass it through this, and then look at the result of the images passing through each of those 32 filters. So if we hit Shift Enter in the next cell, you can see this shows index 1. You can change this if you want to look. For example, if you put index 2 or index 3, that would show you different images. But you can see this is an image of a 2. And this shows you that image of the 2 and the effect of that going through all 32 of those different convolution filters. So you can see like some of them are looking for different types of edges. You know, the third row in the first column that kind of looks like it's looking for like horizontal edges. The second column in the third row, I mean, that kind of is looking like it's looking for like a line-like structure. But each of these is somewhat different. And if we change the index, you know, to 2, we could see a different number. You know, these are 1s, and so on and so forth. Those are 0s. So each of those inputs is going to have like a different effect with those kernels. We could also go back and change this layer to 2. So if we want to look at now we're going to look at the output of that second convolution after it goes through the convolution and the max pooling and the next convolution. Let's look at that. Okay, so it starts to get weirder and weirder the farther you get in the network. But you can see, you know, the output of the second convolution layer. Now this is looking for even like more weirder structure. If we go back to that image of that 2, and we could look at all 64 of them. If you wanted to. Let's see, let's make this an 8 by 8. There we go. So pretty wild. You know, so you can start to look into this network and how your data is being affected by it. Okay, that's kind of the end of what I have. And we're right on time. But what I left you here is 2 more cells so that you could try something of your own. And so I kind of leave that here for you to try something. I worked up an example. It doesn't work as well as the first one I tried, but let's see. Let's grab these. So in this example here, I'm doing those same two convolution layers. I took out the max pooling between them, which is fine. Yeah, I can put that back in. But I changed the dropout to 0.25 here. I put a flat layer then. Then I added a dense layer here with 128 outputs, and then a dropout layer, and then the final dense layer. So you can see I added another dense layer in there and changed the dropouts and stuff like that. You know, I could put in, you know, to make this look more like the other one in the beginning, this max pooling. That looks more like the other one. But then, you know, you could try, see how well this one works. Honestly, with the MNIST data and this kind of structure, they're all going to work pretty well. You're going to see very small changes in the output. But you could try like making really small networks or really big networks and see how that affects the output. I think right away I'm seeing that like, this network isn't really as good. Although no, it's starting to get there. It's taken longer to train, that's for certain. Yeah, how long did the other one take? Let's see. About 4 seconds per epoch, and this one's taking about, oh, that's also 4 seconds. Almost there. If people have questions, you can start putting them in the chat if you want. .4 is what the test accuracy was on this one. What was the other one? Where was that one? 99.2. Oh, I did better. By adding that max pooling layer back in, I got a little bit better. So adding that dense layer improved performance a little bit. Pretty cool. Surprised myself. Can you apply dropouts to convolution layers? Sure. Yeah, you can put them there. Typically, you won't see dropouts in convolution layers. You'll typically see them in the end with the dense layers. But you can see, you know, here in this, the dropout is after this max pooling layer. And so it is happening, you know, where the parameters haven't been reshaped by this flatten yet. It doesn't actually, like the order of the flatten and the dropout wouldn't matter here because the flatten is just changing the shape and the dropout is just gonna drop so many % of these parameters. So it wouldn't change anything there. In fact, it might even work a little bit better because it's dropping out on a 1D array as opposed to a 3D array, but I don't know, you can try it. One thing is interesting, this has 225,000 parameters just by adding that. This other one only had, what was it, 35,000 parameters. So I added a significant number of parameters by adding that other dense layer in there. And you can see that, I mean, there's 205,000 of those here in that dense layer. Crazy.
If you have questions, now it's time to ask them.
That's correct. Else, it is go outside time, probably. I tell my PhD students that, you know, that taking a break every now and then is a good thing, but taking too many breaks is a bad thing. So today seems like a good break day. Can we, let's see. In dropouts, we simply says keep according to probability any way that we can ask to keep which in between probabilities. I don't know the answer to that question. Because the theory of having dropout layers is that you are forcing the network to be hobbled. So it doesn't have access to all of those parameters in the flattened layers. And so it's forcing it to make an inference based on either half or a quarter of the information that it has access to. And so this makes it work better when you want to be able to detect things that are in different places in the image or have different rotations or different scales, because it forces it to be able to make inferences with incomplete data, which is always going to be a reality. So. Any other questions? You're welcome. All right, well, I really appreciate everybody's attention and doing this on a beautiful day, and I enjoy putting these together and always enjoy talking about this stuff. So, oh, Andrew, you got a quick one. Not that quick. Andrew, you still there? Yeah, so if you go to the UCI machine learning repository, you can find all kinds of data sets. And while image-based data are certainly the most popular, because a lot of tasks exist in the three-dimensional world, and the three-dimensional world is inherently represented well with multi-channel imagery, whether that multi-channel is depth, you know, if you consider, you know, a three-dimensional image is just a depth image, or multispectral image where the number of channels is multiple frequencies, like multiple colors, or even bands that we can't see. Most of the tasks that humans are interested in are inherently visual. But there's also a lot of things that we do that aren't, like if you think of like oral tasks, acoustics is a huge thing in deep learning too. So we're doing a lot of work with acoustic waveforms, where maybe it's not even audio, but more acoustic pressure waves using acoustic sensors, basically good microphones, to do inference on whether things exist. Right now we're working with Ford on a problem where we're using acoustic arrays on cars to try to find stuff that's in the environment. For example, wouldn't it be awesome if when your car is driving down the road, that it said, hey, you know, there's a Kirtland's warbler. If you take the next exit and I'll lead you there. Or just told you like, hey, you just passed a Kirtland's warbler, which is a very rare bird. And how do you tell that? Well, if cars are connected, you know, they can act as a big acoustic array. So there's all kinds of ways that you can apply deep learning for not just image data. But often, if you think about any data, it's inherently a multi-dimensional data set. So acoustic data might be in the original pressure wave to be a one-dimensional pressure wave, but if you look at that in the frequency spectrum, like a spectrogram, all of a sudden it looks like an image. You know, it's a big long image that just keeps going and going. But you know, image you can think about as just a two-dimensional data set. An RGB image is, you know, a three-dimensional image. It's just that we typically mix those colors together because that's how our eye sees. So, does that answer your data, or does that answer your question? Cool. All right, any other questions? Okay. Well, it's been a pleasure. I wish everybody great summer if I don't talk to you before then, and a great fall, and hopefully it'll be somewhat normal in the near future. So thanks for tuning in.
Thank you, Dr. Havens, for your wonderful seminar, both machine learning and deep learning, both seminars.
What's that?
Both day 1 and day 2 seminars. Thank you for that. Those are wonderful. And I would send you all the recordings of the seminars, and with that I would attach a feedback survey. So I encourage you to fill out the feedback survey so we can improve our seminars further, and you can have more details of our seminars in our website. Thank you. Goodbye.
Bye.